All right, so welcome. Happy Halloween, everyone. Hope you guys have a good night too and enjoy the snacks as we have our class today. Any questions from material before up to this point? Yes.
I was wondering, I was kind of confused on solving one of the diode questions on the homework.
Okay.
The one that was two diodes with one being inverse. But like canceling the current flow. I was just wondering, like I understand how it works, but how to solve it analytically. So.
It's weird. 10. Oh, whoops, wrong one. That's 11. Okay. Question 7.
Or no, it's 4. Yeah.
This one? Okay.
I'm kind of confused how to do it analytically.
Okay, so you would go through the same process, which is, what do you do to start with?
You would say which ones are on and which ones are off, right?
Okay, correct. So on this then, making those assumptions. I think I might be on the wrong. Okay, like where did it go? Okay, so so which one, like what do you feel?
That one is on and then so that is off.
Okay, so if you assume that one is on and off, then you would, off means what would you replace it with?
Separate from
Correct, so yes, it would be open. And then what do you replace for the on diode? Correct. So keeping the polarity the same direction, which was plus on the left and minus, and then this one was open and it was going the other way, I think. This way?
Yeah.
Yeah. So this would be your VD. So then, so using 0.7 volts because it wasn't given to you, so assume that drop and then solve for the current going through that, which is going to be, correct? And then solve for VD. If you find that VD is actually, I don't remember what the answer was, but VD is less than 0.7, then that one would be verified as off.
Okay. And then that'd be a wire.
Uh-huh.
Right. Or like
What do you mean a wire? Yeah, it would be an open, so current would still be 0 in that one too. So question is, could it be on if you have 0 current?
or
It's questionable. It's unclear, right? So if it meets all the conditions, you could say that it's 0. Let me see what I've had as the solution. 0 volts across. Sorry, say that louder.
Across that diode, there's 0 volts across in your solution.
Uh-huh. Okay. This was 16.
17, I think.
Oh, 17. 16. Yeah. Yeah, I can't read these. 17. No, not 17. 15? 115.
It should be 7.
Oh, yeah, these are renumbered. I think it was 20. Yeah, okay.
4 or something.
Okay.
Okay, that's
Yep. So there's still. So it's kind of questionable, is it really on if you have zero current? So you could make those assumptions, you could go build it, and then you're gonna actually see like, oh, it's gonna teeter one way or the other based on those differences in the voltages and everything else. But it's, as far as hand, you could be like, yeah, I'm gonna say it's on for 0. Okay. All right, any other questions? Okay, you guys ready to jump to the next material? Okay, transistors. So transistors, so fun. We're gonna actually start with a little video because it does it more concisely than I do. Okay. Okay, so this is going back to the diode, and remember when you have the charges, you have the plus and the minus little barrier. And then if you apply a external source, if you apply it in the same direction as that plus and minus, it depletes more, so you get a bigger region and no current flow. And then when you flip it, it's gonna flip, then you have the attraction of the electrons and are going to be moving more. And again, they're occupying those holes that are right by the depletion layer. And now they continue to jump and you have an increased amount of electrons, so you get that flow of current that goes through. So this is the forward biasing effect. This visual is much better than my drawings, so there you get the current flow. So the reverse biased and the forward biased, reverse biased, no current flow, forward biased, you have current flow. So now what we're doing is we're creating 3 layers. So you have an N, P, and N type. So you have diodes, a PN that's reversed, and then you also have an NP that is the normal flow. And so this is the transistor itself. It's a BJT transistor. And in the BJT transistor, if you put on voltage actually between that base and emitter, you actually get a forward biased diode there. And so it flows just like the normal one. You have flow of electrons that go from the base into that emitter. And so the electron flow happens and you get current that actually is flowing. Again, these are the electron movements, so the current's flowing actually into the base. And then the remaining electrons, you have what's called a beta, and depending on that beta, you actually get a flow of electrons that you can see here from the collector through the battery. And so the electrons are moving through from the emitter. Some of them go out the base, and then most of them go through the collector. So you can see that you have a much higher flow between the emitter, or the collector and the emitter, and then there's a little bit of flow at the base. So this acts kind of like a switch, and then this is the actual symbol of the BJT, or the actual. Okay, I can't. There we go. Oh, where did it go? Okay. Oh, no, did it again. Okay. So this is the actual little device that you're going to see. So it has 3 connectors on it. One is your emitter, the middle one is the base, and then you have the collector. And the flat side of it is where you can read which is which. So collector's always going to be on the right side, and then the emitter's going to be on the left side, and base in the middle. So those are going to be your three connectors. And then we're going to look at this in the form of an actual element. So goals today: identify an NPN versus a PNP transistor, understand how this transistor works. There's 3 modes of operation. And then understand the directions of the flow of current. And then understand the steps in solving a circuit that has this transistor in it. So those are our goals that we're going to achieve today. Okay, so here is a side view of the transistor. So this one is called an NPN. And on the NPN, the top part is N, the middle part is P, and the bottom part is N. Remember in that there was between the P and the N, you have a diode, and so that's what that arrow is representing, is that diode that's working in forward. So this is how you identify if you have an NPN or a PNP. So that arrow is also on what's called the emitter side. And so you can remember which side's the emitter by the arrow. And the other side is the collector, and the middle portion is the base. So these are our 3 connectors. And then you have these voltages. So VBE means the first variable number, or first variable letter, so VB, and then you subtract off the second one. So it's a voltage difference between the base and the emitter, and mathematically it's VB minus VE. So VCE means what? Correct, VC minus VE, and VCB is? Correct. So that means the plus side is the first one. So in this case, VCB is a plus to minus. VBE is the plus on the base side and minus the emitter side. And VCE is the plus on the top and minus on the bottom. So when we analyze the circuits, you'll want to remember that so that you can label your polarities correctly. All right, current in here, as you saw, the electrons were actually moving out of the base, which means the current flows into the base. And then it flows from the collector side down to the emitter side. All right, questions about the symbol, locations on it? Okay. All right, so looking at where you may use a BJT. So for you guys, this is a motor. I can spell motor. Okay. And an Arduino board. And so a lot of times you want to hook up the motor to an Arduino and make it run and do something. So, sorry. Trying to pull up my notes for this one. Okay, 17. Okay. Sorry, this is not matching my notes. I'm like, where am I? Okay, I'm gonna try and remember this offhand. So the Arduino has some specs related to it. Oh, there it is. Okay, that's why, 21. Okay, now I found the right one. Okay, the specs of the Arduino, you have 5 volts. But the thing about the 5 volts is that it's limited, so it can get to be 20 milliamps or 40 milliamps, depending on which pin you're actually using. Anybody know motors, like what they need? Yeah.
At least an amp.
Okay.
Like the beat.
Okay, so you need at least an amp. Voltage, anyone know voltages? Typically they're higher than 5 volts, so sometimes you may even need, 12 volts is more common. So looking at this motor, we need 12 volts and an amp, and our board only puts out 5 volts and 40 milliamps at the most. So what can we do to actually get more current and more voltage in a safe way? So that's where this transistor becomes very useful. So we can actually put a 12 volt supply, put our motor here, and then connect it to this BJT and have the Arduino. So if you want to visualize how this transistor may work, one way to think about it is that that base is the control, and depending on what value is at that base, it acts like kind of like a knob for like your faucet, where if I turn it on a little, I get a little bit of water out. If I turn it on a lot, I get a lot of water out. And so it can be variable like that, just like a faucet handle. Or you can use it in 2 kind of modes, like, oh, I just want it on or off, which would be more of a switch mode. So there's 2 different kind of modes you can use. One is that variation or variable amount. It's non-linear, so it's going to be up in an exponential form as it moves. So if I move it a little bit, it actually responds more exponentially. So it's hard to do a linear change to it, but you can approximate a linear change. So most of the time, you either want it to be on or off. You can then use that resistor that's connected at the base to control how much it's on and how much current will immediately go to the motor. So with this being hooked up to 12 volts, that can supply as much voltage as you need for the motor. And then it also, once it turns on, creates a short circuit almost. And so you get as much current as you want drawn from there too. So you can actually draw more current if you want to add different resistors in there to add on to or put in parallel to the motor, so that you can actually control that amount of flow of current through it too. So this is a very useful circuit that you can use to be able to hook up the motor. So this resistor to control amount. So how this, another way to kind of visualize this is that it kind of works, so it can be on off, and when on, it's more like a potentiometer resistor. So depending on how I've turned it on, it acts more like a potentiometer, and then that resistance controls the current flow through that branch through the motor. So it acts like a potentiometer resistance. So that's one other way that you can kind of visualize this. Okay. Okay, so going back to the transistors themselves, so we already defined like this is an NPN, so it has the little arrow. What is this side of it? Arrow is the what? Thank you. Emitter side. So that branch is emitter, and so we label this as a VE for the voltage at the emitter side. What's the top part? Oh, I didn't block those out. Okay, collector, it's already there. VC, and then what will be the variable at the base? Variable at the base. Thank you, VB. Okay, current go in or out of VB at the VB location? In, correct. And down or up for VC? Down. And then down or up for VE? Thank you, down. Okay, so VB turns it on, and then the majority of the current flows from the collector to the emitter. Okay. Then we have the differences. What would you assume, knowing that this is a diode, what do you assume this voltage is going to be? Correct. So we make that assumption that it's 0.7 volts and it's acting like a diode. So we use that to actually solve this circuit. Then this is the PNP. So the difference between the PNP, what do you notice is the difference here? Correct. So the diode actually is in, and so that is how you differentiate it. If it goes in, it's a PNP. The side of the arrow is still the emitter side. So sometimes in circuit diagrams, you're going to see this flipped upside down and drawn this direction with the arrow still going in. That will be the same. So this would be a PNP. And this is still the emitter side. This would be the collector, and this is the base. For a PNP, the current goes out from the base. So this would be IB. I forgot to label these. So you label them still with the same variables. So IE, IC, and IB. So IB goes out, and then the current goes down from the emitter, or if it's drawn upside down, then it would still go from it would go up in this case, from the emitter to the collector. VE and IE. Okay, so PNP is kind of opposite the NPN. Currents go in to the emitter, and then they flow from collector to emitter, and then for the PNP, they flow the other way, and the current goes out. All right, questions on how to identify NPN versus PNP? Okay. All right, so we're moving on to the regions of operation. So as I said, there's 3 regions of operation. The first one is cutoff, where it's open. So this is going to be where it's pretty much open, it's off. When it's open or off, it's open. So your I is going to be 0 flowing through it. So you have no current flow. And your condition is that diode VBE is less than 0.7. So all your currents, so maybe I'll differentiate this better. Oh. So IC is equal to 0, and IB and IE, all of them are equal to 0. So no current flows in the circuit. So the check on this, we're going to do this just like the diode, where you make an assumption, you analyze the circuit with those assumptions, and then you check. So this is going to be your check, is that VBE is less than 0.7, and that diode is off. Okay. For active, which is what we use for the analog region, you will use an assumption that 0.7 or VBE is 0.7, and then you're going to check that VC is greater than VB. And that will be for the NPN, but it will be opposite for the PNP. So this will be your main check once you've solved the circuit with IBE equal to 0.7. We can use another, so we use the VBE equals 0.7 for this case. And we also use a condition that they are proportional to each other through, or the currents are proportional to each other through this beta. There's one more term called alpha, and that's beta over beta plus 1. So you may be like, well, what is beta? So beta is a property of the BJT based on the doping that it has, and it can range to purple anywhere from 40 to 400. And it is a and it can even be 20 for what we call power transistors. So it's the number of electrons making it across the collector. So the higher the number, the easier it is for those electrons to come across. So if I put on 1 into the circuit, it is actually multiplying it, all those electrons. If the beta is 100, it's multiplying them by 100. If it's 400, it's multiplying it by 400. So it has to do with the doping in the material itself to say, well, what is that amplification of whatever I put on the base? How much is it amplifying into from that collector side? So typically, if we don't know something, we make an assumption. So 100 is kind of I use 99 because that's even easier when you do 99 plus 1 is 100. So you can make an assumption when you use a hand calculation. To find what beta actually is, you would have to go measure it in the lab, because for a batch of transistors that you may just buy, they're going to vary from batch to batch. So as I said, one of them may be 40, one of them may be 400. So they're going to vary each time they are made. And so you would have to actually measure them specifically. So we try to make the design as electrical engineers. You usually focus on making that design not to be varied that much by the beta value. And there's different techniques for that, which the E side gets into. For you guys, you just need to know, like, be aware of that. So if you have a board that you're like, okay, that BJT broke, need to be replaced, hand it off to somebody to replace it for you, and you get it back and you try and run your motor again and you're like, this isn't working, this could be a reason why. Is that the beta that they transitioned it over to could have a different beta, and therefore then it's now giving you different currents, different voltages than you would have expected in the first place. Does that make sense? Yes?
If you have one that breaks, is there a way to test it, or is it just kind of have to guess from there what you had, or you usually?
Yeah, once it's broken, it would be hard to know what the beta was. So as I said, most of the time you guys are going to be using them more for like an on-off switch. So beta is not going to come into play there, but the current could vary quite a bit even in that on-off situation. So you would be like, oh, I'd still need to make sure that this is 1 amp or close to it so that it's still turning on the motor to what you need. And in that case, you would have to just try out different betas or different transistors to be like, oh, this one may match, that one may not. So, all right, so this would be the analog. And then as I said, saturation is going to be a lot of what you're going to look at where it's just on or off. So in this case, it would be what's considered fully on. And in fully on, you use the assumption again that VBE is 0.7. But to solve this, this condition is no longer valid. So you can't relate the currents by that beta value. Instead, you have to just assume that there's a fixed voltage between the collector and the emitter now that you're in this fully on state. So instead, you use a VCE value. And VCE is also dependent on the doping, so it can vary from 0.2 to 0.7. And it will have its range on a data sheet typically for the batch that you have. And so if you use a specific QN, whatever it is, you would have it on a data sheet, a range of what it would use. You could use a mid-range of it, or if you're looking at more extremes, you could use the higher or lower depending on which one's going to give you the worst case kind of scenario. For this check, you're going to check that VC is now going to be less than VB for an MPN. And it will be greater than VB for a PNP. And then in saturation, you have a beta, but it's now called beta forced. And you want beta forced to also, I should do these, this is a check. So I'll put beta forced. Needs to be a lot less than beta. So if my beta is like 99 and I calculate the beta forced, and you find beta forced by finding the IC value that you solve for over the IB value. So say I had beta is like, okay, you're given it, you make an assumption that it's like 99. You solve your circuit using that beta, and you find it's not in the, and you assumed active, it's not in active mode. So you move to saturation, you resolve the circuit, and you find that your IC and IB values, you calculate this beta forced, and you find out it's 98 instead of 99. This would mean that you're right on the threshold between the two conditions where it's partially on, a little bit less than partially on. So in this case, it is a smooth curve, so they don't jump. So it is a smooth curve, and what the characteristics of this is it's going to be acting in between kind of both. So it won't be fully on, but it won't be fully off. But the current that will flow through there, which is usually your major concern of what you want from it, should be the same because it's a continuous graph. So whether you solve whichever method you use to solve it, it's actually going to be pretty close to either value. And you'll find they'll be off a little bit by a hand calculation or a simulation. But then when you go measure it, you're like, oh, well, the current's close to what I wanted. So it doesn't actually end up mattering if it's that close. You say that you're well into being on if beta forced is at least 10 times less than that. So if it's 99 and you get like 80, then you're like, okay, well, I'm well into this on phase, and it really is just going to be calculated using the saturation steps. Was there a question? Did you guys have a question, no one?
No, we were just going to say we couldn't see.
You couldn't see it? Okay, sorry. All right. Okay, any questions so far? Okay. So steps for solving when you have DC voltages and currents in a BJT circuit. So these notes are from electrical engineering course that I teach. So in that case, we're always looking typically at the analog, which is going to be an and you can use these to actually make an amplifier circuit. So we use them in that way. So that's why this note is saying, assume transistor is in active mode. For you guys, you may always want to assume like it's on or off. And so you're going to start off with the saturation mode. So this could be either mode. So if you assume it's saturation, this will be, if you assume active, you're going to use VBE as 0.7. And also, actually for saturation and active, you're going to still use for saturation the VBE equals 0.7. And either way, you're still going to solve for the BJT node voltages and currents. If it's not easy to find exactly at the base and exactly at the emitter, you're going to do a loop always from the base to the emitter loop. Because you now know VBE, so that's a known value from the base to the emitter. So it would give you a loop of known values. You can also find a Thevenin at any node. So say you have a pretty complicated circuit at the base and you're like, wow, I don't have any clue what to do. With that, you would disconnect the transistor from that more complicated circuit and then simplify that circuitry into a Thevenin equivalent. So you would find the resistance of it and the voltage of it. And then you would use that as the base circuitry. And then it becomes much simpler. Same thing could be happening at any of the other nodes too. You may have a more complicated circuit, so you disconnect it from whatever it's on to the transistor and then find the Thevenin of that portion. Okay, for the active mode, you can use this relationship as one of your equations. So IC will be equal to beta IB is equal to alpha IE. After solving those for the currents and the voltages, you're going to then check if VC is greater than VB or even equal. You'll be in the PN, or the NPN will be the correct value. So this would be your check. So check. And then if the solution is not that value, then you would say like, okay, now I need to go to either it's off, cut off, solve all of the currents, set to 0, and then what do you check for if it's off? Anyone remember? Okay, good. So with this one, you're going to check that VBE is less than 0.7. And if so, you're like, yes, it is off. If it's not, then you would assume the third case, which would be saturation, and solve it using VCE is approximately 0.3. Again, that could be 0.2, 0.5, 0.7, anywhere in between 0.2 to 0.7. And then VBE equals 0.7, so these two values are what you're using. And then for this one, for an NPN, we can sum up the currents. So you know that your base in and your collector in is going to equal your emitter. So remember the current flows, IB and IC. And so those two combined equals your IE. So you can use that summation as another equation. So those three equations you can use. And then you can solve for the voltages and currents. And then for this one, what is your check? When you're checking for saturation. for an NPN?
VC is less than VB.
Correct. So you check that VC is less than VB. And then if it is, then you're like, yes, this is saturated. Okay, any questions about these? Okay, we're gonna jump into problems. Okay, so looking at this one, if you have nothing connected to the base, what happens, do you think? Any thoughts? Correct. So what would you assume the transistor is going to do? Which would be 0, which is off. So you would say it's off if there's nothing connected to it, it's just sitting there, it's probably off. So we would assume off, and what does it mean to be off with the currents? Correct, 0, 0. And then VC would be what here? 12 volts, correct. Okay. Another thing that you may find is that you may really want to be careful about the power, because that RC may be like your motor there. And so your motor can only handle so much power also. So you'd also want to be cognizant to try to calculate the power. So, and the power across the transistor. So this was 0, and then this was 12 volts, and this is 0. So what would be our power here? Okay. It would be 0. And the reason it's 0 because your VCE is 0 in this, or is, that's not 0. VBE. Sorry. VCE times IC. So I'm not going to go into a lot of detail, but your power in your transistor is going to be, majority of it is going to be from the current flow of IC because it's the majority of it. So that's just one way to kind of make an approximation that I won't go into detail about how to actually get the detailed power, is to just look at the current in the collector, and then you're going to take that VCE times the current in the collector. So when you have actual current flow instead of the 0 current here, you would get that. To be a little bit more detailed, and again, I'm not going to go into the details of this, but it would be VCE times the IC plus the power that actually is being, because you have the two components of it. You have across the collector and the emitter, and then from the base to emitter, you also have an element that's going to consume power. So you have to actually add both of those together. That's a simple way to put it. Okay, so this is the actual equation that you're going to look at is both of those, but if you want to get just a rough estimate quickly, you could just look at the current in the collector and then that voltage across it. So in this case, the voltage across it would be 12 volts. So if we had quite a bit of current, that's actually a lot of wattage that's going across that transistor. So you have to be careful about that also. So looking at the power, you may need to know the power for the motor if you put the motor where the RC is, and then also the transistor itself so you don't blow it up. You may also, if you are drawing a lot of power, you may want to use heat sinks. So you want to be cognizant that there are heat sinks which will draw some of that heat away too. All right, let's look at this example. So now when we have it closed and we're assuming beta is 100. Our first step is to make the assumption of something. So let's do the active region first. So we're going to assume it's active, and when we assume it's active, we can use the equations that 0.7 between B and E, and then we can assume IB is or IC is equal to beta IB. And then, well, we'll just go that one's easier. So since we don't have any circuitry in the emitter side, we're just going to look at the collector and the base side. So with this, we can draw here between this voltage here and this voltage here, we're putting a known value of 0.7. And then where did I say you have to take the pathway? This is key. Take the pathway from where to where? So it's not labeled here from the voltage to the emitter, but this would be an unknown between the collector and the emitter side. So you can't just skip over the transistor. You have to know the voltage on both sides of it to analyze it with the electrical circuit technique. So without knowing what voltage is between the collector and emitter, that becomes an unknown. So you want to avoid that pathway. So instead, you're going to take, where's your pathway that you know a number? Okay, so this goes from here to here, right? This is kind of from ground to that point is 5 volts. Then I kind of know all these, and then I have a choice of going up. Again, I don't know those values either. So this would be VC. That would be VCB, again, an unknown. So I want to make sure to take the pathway through that 0.7 that I put on, and then I get to ground. So that gives me a loop of all known values in there. So the key is to take the pathway from base to emitter or emitter to base, but between those locations. Okay, so that's key on active. All right, so when we do that, we have IB is here. So I have and this is plus to minus at ground, so a plus, minus, minus, and then I'm back to ground. So plus VBB minus IB 5K minus 0.7 equals 0. And I can solve this for IB. IB is 5 minus 0.7 over 5K, 4.3 over 5K. So this gives me, what does that give me? 0.86 milliamps. And then from there, we can use the relationship to get IC, because we still don't know VCE or VCB. So IE is going to be found by the beta IB, and at 100, this will be 86 milli. So how do I know if these values are correct or not? Yes, one more step before I go there then. What is VB? Correct. VE? VE's right here, right? At ground, so it's 0, thank you. Okay, VC, it's not easy to look at VC and say exactly what it is. So you're gonna have to take a loop there to find VC. So VC is from that location to ground. So my pathway goes through the VCC, through there, and then through VC there. And again, remember that is, in relation to ground. And in relation to ground. So this would be plus VCC minus IC times RC, and then a minus VC. So I'll do these as this plus VCC is 12 minus IC times 100 minus VC equals 0. And so 12 minus 86 milli, 86 milli times 100. So this gives me a value of VC of 3.4 volts. So found IC, IB, VC, VE, and VB. So now what do we need to check? I still have some confused looks though. So questions? Yes.
So IC equals IE on this one?
Oh, sorry. I miswrote that. This should be IC. Sorry, that is IC equals beta IB. IE will equal 100 over 101 times 0.86 milli. So it will be very close to that value, but so a lot of times you can make an assumption that they're very close, but it should be IC equals beta IB. Sorry, that was a miswriting on my part. All right, other questions? You guys following this? Yes.
Sorry, can you scroll up a little bit so I can see what you did on the second part?
So, this is going to be 85 milliamps. So, very, very close. All right, so what do we have to check now? So, as long as you guys followed me with how to get those values, what do you check? Okay, so correct. Is VC larger than VB? And we have 3.4, and VB is 0.7, so yes. Yes, it is. So that would be like, yes, this is a correct assumption. Okay? Yes?
What would happen if it's, like, if you were to do all this work, and then you check, and you're wrong, then does that mean that we have to go through the cutoff and the saturation afterwards?
Correct. Yeah. So yes, if you did this by hand and you're like, oh, VC is actually less than VB, then this is not the correct assumption. So then you reanalyze the circuit, you start again from the beginning. You'll notice the loop will be the same because VBE will still be 0.7. So that original loop will be the same between VB and VE. And then it will just be that you can't use the IC equals beta IB. So that's where the difference goes. And then you would use a summation instead of IB plus IC equals IE. And then you would also use a value for VCE and take a loop from VCC down through to ground. And so those would give you two other equations to be able to solve it. Okay, other questions? Okay.
Are you gonna go through an example where you can do saturation and cutoff?
Yes. Well, cutoff we already did. It's very easy.
Yeah, that's
That one's the easiest because you're like everything's zero. So whatever the voltage is on there, that goes to that node, and then everything else is zero. So that one's usually the easiest one. And then this is active, and then, yeah, we'll go through a saturation one. Okay, so in this one, we're going to assume saturation instead. And with this one, we're given beta is 200. And then we also need to know VCE. So we're going to do a VCE is equal, let's see what the numbers solved it as. Oh, sorry, backing up 1 second. I forgot to calculate the power. So we're going to, what will the power be here? It will approximately be what?
VCE times IC.
Correct. VCE times IC. And in this case, what is VCE? Correct. 3.4. And then IC. Thank you, 86 milli. And so multiplying that out gives me 292.4 milliwatts. All right. So yes, it's quite a bit of power being consumed there, but that still might not be a big deal. But you do need to check the capability of whatever device you're using. So you would look on a data sheet and it would have a max power rating on it. Okay, so moving now to saturation. So in this case, you're given that VCE is 0.2 volts, yes?
When are we allowed to use the smaller power equation? Good.
It's easier to do by hand.
Okay.
So just use that one. So as you notice here, like you're only getting 1 milliamp, approximately 1 milliamp out of the IB, and then you get 100 times that for the IC. So, you know, you're a lot larger. So if your beta is maybe 40, you might be like, I probably do want to maybe consider both those.
Okay.
But if you have a high beta, then it's going to be so much more dominant that you're going to get, you know, again, it's times the IC and the times the IB. So if you're a factor of 100,
Okay.
still going to be so dominant that you're like, this is way easier just to calculate.
Okay.
40, you may be like, I probably want to calculate both those. So I'm going to do the smaller amount too.
Okay.
Does that make sense?
Yeah.
Okay. You guys might like me a lot. I like hand calculations and then go use the simulator to get like your actual better values. So that's the better way to do it, is go simulate this and actually use those simulation values instead of your hand calculation. But as far as designing, usually by hand you get an approximation of like, oh, I probably want to start with this resistor in there, because that's going to give me a ballpark figure of what to do for the design.
Okay.
All right, okay, so saturation now. So we need to know VCE in this case. So we're going to assume saturation this time. And so our assumption is that we can use this VBE as 0.7. And then we use the VCE, which goes here to here, of 0.2. So this is the difference between the saturation and the active mode, is that we have to use the voltages now, and we don't have a relationship between the collector and the base. So pathway is still going to be the same. You're going to come through the pathway here. So minus to plus, so plus, and then this is going in this direction, IB, and then a minus. So plus 5 minus IB times 5K minus 0.7 equals 0. So IB is again going to be the 0.86 milli that we found from the previous one. But now we can't use that relationship of IB equals, or IB times beta is equal to IC. So instead, we're going to have to take a pathway on the top. So here we take a pathway through this loop. And so do, plus to minus, and then, so this is a plus, minus, minus. So plus 12 minus 100 times IC minus 0.2 equals 0, and then we can solve this to get IC. So 12 minus 0.2 over 100, which gives me 118 milliamps. All right, VC will be what? Okay. 0.2 volts, correct? And put them here, I guess. Let's see, green. 118 milliamps, 0.2 volts. IB was 0.86 milli. VB is correct, 0.7 volts, and now my power is what? Power is approximately it's what? Okay, how did you get that? It is? But E is ground, right? So VC is VCE.
I did 0.2 instead of 0.7.
It should be 0.2.
It is.
It is right, yeah. I was trying to give you, yes, you're on the right track. So VE is 0, so VCE will be just the 0.2. So 0.2 times 118 milli gives you about 23.6 milliwatts. So take away 23.6 milliwatts versus 292.4 milliwatts. Same circuit with different components, or same components. Oops. Which one's better? This one, right? Less power. So the only thing we need to check is this on, then the saturation or not. So takeaway is that saturation consumes less power. So as I said, for you guys just trying to turn on and off motors, this is going to be a better way to make sure it's in the saturation region, and you don't have as much power consumption. So if you can, you try and use saturation mode to use this. So let's just check. What do we need to check here?
VC is equal to VB. Oh, whoops. VC is less than VB.
Correct. So we need to check that VC is less than VB. And VC is less than VB. And in this case, 0.2 is less than 0.7. So yes.
Did we just assume that that VC is always gonna be 0.2 when it's in saturation, or am I getting that from somewhere else?
You can it's actually accurate to say 0.2, 0.5, 0.7, whatever number you want to use in between 0.2 and 0.7.
Okay.
So a data sheet will have like a range on there, usually just like 0.2 to 0.7.
Okay.
So I like 0.2. So it's an easier number to work with.
So what does that mean? So if VC if there's more voltage going through the collector, does that mean that it's going to consume more power, essentially?
Say that again. If
If there's more voltage going through the collector, at least assuming it's in saturation, does that mean that there's more power that's going to be consumed?
yeah.
So
So you would have more power if it's 0.7, but not as much as if it's in the active region. Because the active region, it won't depend on the characteristics of the transistor. It's going to contain, or it's going to, can't talk now. It's going to be related to the external circuitry, which usually has higher voltages and currents going through them. So that's why. All right, so beta forced is going to be IC over IB. And in this case, 118 milli over 0.86 milli. And so you end up getting 137. So the 137 is actually higher than 100. So if you had assumed beta was 100, you would actually be very questionable if this really was staying in that saturation or not. If your beta is 200, then 137 would be accurate to say, yes, I'm in saturation. So depending on your transistor, this circuit could be in active mode instead of this saturation. So that's another thing you kind of have to be careful with, is even if you design it, you're like, oh, that's actually still in the active region and I'm consuming a lot of power. So the lower number you use, the more likely then you could design it to be in the saturation region. How would you, so say this is like beta is 100, thoughts on how you could actually make this into saturation by changing something on here? What is going to control whether it's in saturation or not if your beta is 100? Any thoughts?
Change RC.
Okay. So RC would definitely change it. So if you increase that, then your VC will be lower, which is what you would want to do. But if you increase RC, then you also have more power being consumed in that resistor. So there's always like a little bit of a trade-off that you have to look at. Okay. Lowering the voltage, VCC is 12 volts. Lowering that voltage would also possibly lower it. Again, the risk there is, do you have enough power to your motor to turn it on? So some other things to think about as far as being able to do that. Okay.
Is RC required, like having a resistor there?
So that's representing your motor. So that's actually representative of your motor, and your motor will have some, it's actually an inductance and the resistance there, as I showed last time. So We're ignoring the inductance part of it for now, because when you look at it just in DC, remember, you don't have any change in the times, so you're going to look at that as a wire for the inductance, so we usually just look at the resistance in the DC side. But that is representative of that DC motor. Okay. So on this one, assume active. And solve for your currents and your voltages. And use, trying to see what beta was used. Use beta as 100. I don't know what happened to my. Sorry. Okay.
Right.
All right, we're running out of time, so I'll just go through this quickly. Okay, so pathway is from where to where? Do you want to start with your pathway? So you're going to take it through this, right? So you label the 0.7, so that's what you assume when you're inactive, that VBE is equal to 0.7. So this is plus to minus, and then you also have IE here from plus to minus. So a plus minus minus, so plus 3 minus 0.7 minus IE times 2.7K. So solving this, we get 2.3 over 2.7K, which gives us 0.825, or point, I can talk, 0.852 milliamps. And VE, so we have VB is given as 3 volts, and then VE is 0.7 less than that. So 2.3 volts. And then we need to know VC and IC. So we can use a pathway here. This will be to ground, and then plus to minus, so plus, and then a minus, and then again this goes to ground of a minus. So our loop is 20 minus IC times 10K minus VC. And then IC is equal to IE by beta over beta plus 1. So IC will equal 100 over 101 IE, which ends up being a 0.84. And so solving this for VC, we get 20 minus 0.84 milli times 10K. So this gives us VC is approximately, actually I don't have it. So 20 minus 0.84 as 8.4 milli as 16.4. 11.6. There we go. So is this in the active region? What do you need to check? Correct. And so 11.6 is greater than 3, so yes. So this would be correct in that it is in active region. Okay, I'll solve, so this next saturation problem is actually a little bit more complicated, so I'll solve it and then I'll post it on the annotated notes. All right, see you guys on Tuesday. Have a happy Halloween.
Thank you.